Great. I think it's recording. Awesome. Okay. So, hello, everyone watching. I am Sofía Martínez Alberga, and I'll be talking to you all today about loops and homotopy. And I want to give some context to the work and the notions that I am going to be discussing today. So let me start by saying some motivation and where exactly this work lies in the grand scheme of mathematics. So the things I'm going to be talking about today lie in the area of algebraic topology. This is a theoretical area of mathematics that, as the name suggests, combines algebra and topology. If you don't know what topology is, that's fine. I'm going to give you some idea of what it is. If you don't know what algebra is, maybe more abstractly, that's also fine. The thing you should think about when I say the word algebra is something along these lines. So it's an area of study which deals with sets, which have operations satisfying certain compatibilities that are really expressed as equations, right? So here I've described for you a set, G, with elements E, F, G, and H, such that they satisfy certain compatibilities. The first one loosely resembles something called associativity. The second one loosely resembles the idea of having an identity element. And the last one, something that resembles having an inverse. And this is the way I like to think of algebra more generally. So you have a set with some operations, and you want to understand how these operations interact with one another and how they interact with the elements, right? So this is what one should maybe think of when we talk about algebra. When we talk about topology, we are really talking about a study where we study spaces, which are expressed as sets, and there's a notion of nearness, and there's a notion of continuous transformations between these sets. So here I've drawn a little schematic for you. If I have a space or a blob X and I have some other blob Y, I can study how these epsilon balls or delta balls covering the space move or transform or change across continuous maps. This is a general philosophy in topology. So with that being said, let's kind of discuss the goal of algebraic topology. So the goal, generally speaking, is to use the algebraic structure that I just described for you and use the robustness to study spaces, topological spaces, up to some notion of equivalence. So to classify spaces for whatever it means for two spaces to be equivalent, right? And I'll get into more of what all these words mean throughout my talk. So let me give you an outline of really what I want to discuss. I want to discuss loops and loop spaces. This was in the title of my talk. I want to discuss an operation that we can define on loops. I'm going to call it products of loops. Then I'm going to talk about homotopy and more generally homotopy groups. And lastly, I'm going to talk about some of my research and how it relates to all these notions described in 1 through 3. So let's talk about loops and loop spaces. First and foremost, what is a loop? A loop, given a topological space X and a base point is just any point you choose in your space. A loop is going to be a continuous map. I call it here alpha. I'm going to call most of my loops Greek letters. Alpha from the interval to the space. And I ask that alpha 0 and alpha 1 are both the base point, are evaluated to the base point. What does that mean? That means the image of my loop alpha really looks like some twisty, turvy, circly thing in my space. But again, it's a map from the interval to the space where you start and finish at the same place, mainly the base point, right? So here's a schematic. I'm going to draw lots of pictures like this today, so becoming familiar with the fact that a loop is really a map, right? So it's really these sorts of arrows, but its images look like our intuitive notion of loops. An important loop for us is going to be the constant loop, the loop that doesn't travel anywhere. So this takes the entire interval to just the base point itself. And you might hear me say throughout this talk that this interval is kind of like the time interval. It tells you where to travel in the image or where to be in the image of your loop alpha, right? So I might interchange these words. And I'm also kind of implicitly calling it time when I assign t to some value, right? All right. So with that being said, it's reason to believe or reason to suspect that you can study all loops, every loop ever, all the maps from the interval to your space. And that's defined to be the loop space. So given a topological space and a base point in that space, I define the loop space with respect to this base point to be another topological space, so another blobby thing, um, consisting of all the loops in X based at that space, right? So now I'm studying a bunch of maps, and I wrote it for you here in set notation. Should be studying maps from the interval to the space where you start and finish at the base point. And this new topological space sort of looks as follows. This is, again, just a schematic. The points in your space are loops, and this new base loop space has a base point itself. In fact, it's the constant loop. And if I were to study loops in this space, this would be a loop of loops, where each point in this squiggly thing that I just drew is a loop. We're not necessarily studying that today. We're studying loops in the topological space we started with, right? So this is an important point to keep in mind, that when we're trying to visualize the loop space, we're not drawing loops there. We're drawing points that represent loops. So this alpha is this alpha that I was depicting before, and beta is another loop that looks like this, and so on and so forth. Okay, fantastic. Moving forward to products of loops. So now I want to discuss some sort of algebraic product, namely an interesting binary operation on the loop space. So if I give you two loops, how can I achieve a third loop, right? That's what a binary operation is. It takes two elements of your set or group or so on, and it spits out another element, just one element though. So the idea is as follows. If I have two loops, two maps from the interval to the space, both finishing and ending at the same spot, right? How do I define the product of loops? How do I get a new loop out? And this is the way we do it. I can say, okay, well, they both start and end at the same place, namely x naught, right? And what if I do alpha twice as fast, right? This is the time thing I was referring to earlier. What if I do alpha very quickly in the first half of the interval, and then I do beta? Well, that's a loop that starts and ends at the same place, right? Because alpha and beta started at the same place. Great. I should note that for the remainder of this discussion, I'm going to use diagrammatic things as follows. So again, for the first half, do alpha, run the course alpha runs, and then for the second half, right, I'll land back at x naught. I'll do beta twice as fast. So I make it back to x naught, right? So this is the schematic I'll be using, alpha, then beta, and it might get confusing later, but whatever comes on the right of this symbol, right, star, pink star, will go first, and then on the left-hand side, that's the loop will run second. With that being said, I want to also remark that the image in X of alpha loop or alpha loop product beta is going to look just like alpha and beta. So this time parameter is not being reflected. It's really being reflected simply algebraically when we write the symbols, but pictorially, the images are going to look the same. I can't write on paper how much faster I'm doing alpha than beta, but this is just an aside. With that being said, I'd like to ask some more interesting questions about this new loop product that we've defined. Additionally, I would like to say that sometimes in the literature, this loop product is called concatenation of loops, because you simply join loops together. You do one loop and you do the other loop, just linking loops together is really what you can think of this as. So what are some properties of this new product that I've defined for you? it's natural to ask of a binary operation like the one I just defined for you, does it satisfy some nice equations like I described at the beginning? And the answer is, maybe, maybe not, but the ones we ask are, generally speaking, can we change the order of operations? Can I simply flip alpha and beta and get the same loop out? And can I associate, right, different pairs of different pairwise products, right? So this is the notion of associativity, and this is the notion of commutativity. Can we flip things around? Can we do one thing and then the next? And is that the same as doing the next thing and then the one thing, right? And these are sorts of questions we like to investigate when we're talking about binary operations. So let's do that now. Is it true? The question is, does this operation admit flipping of elements, right? So let's investigate. The left-hand side of what I've written here is the thing I've drawn, right? So you do alpha for the first bit and then beta for the second bit. So alpha for the first bit, you land back at x naught, beta for the second bit. And the right-hand side is we'll do beta first and then do alpha, right? And the answer is no, unfortunately. Why? Because when we study functions, if we ask two functions to be the same, then what happens? What needs to happen for two functions to be the same? Well, they should evaluate to the same points everywhere. And unfortunately, they're only evaluating to the same points at 0, halfway through, and at 1. In this entire first half of the interval, it's evaluating alpha, which isn't necessarily the same as beta, and vice versa in the second half. So unfortunately, this is not an operation which admits commutativity, right? Sadly. So let's ask the similar question for associativity, right? We have commutativity. We said, no, it doesn't quite work. Does it work for associativity? Let's draw our pictures again, right? So the left-hand side looks something like this, where at first I did alpha and beta, right? And then I concatenated with gamma. So I'm doing gamma for the second half, but in the first fourth, I'm doing alpha, and the second fourth, I'm doing beta. The right-hand side looks similarly. First, I do alpha, then I do beta for a fourth, and then I do gamma for the last fourth. And we investigate again, does it hold that these two functions are equal to each other? Well, not quite, but now there are many more points where these two functions are equal to each other, right? Where these two loops are equal to each other. Namely, this fourth is the same as this fourth. This fourth kind of got moved a little here. And this fourth is still here, right? We just kind of shrunk the half down. So now there are many more points where these functions are the same. So they're not exactly equal, but almost, right? What is this but almost about? Let's investigate what's actually happening. It turns out that there is a continuous function from the domain of one loop to the domain of the other loop. What does that mean loosely? It means I can sort of drag these tick marks along over the course of an interval, essentially, and get the loop before. So I kind of shrink the time that I do alpha and I increment the time I do gamma to get the other loop. This is very interesting, and it's manifested itself in many ways, and it's interested mathematicians for a really long time. So it's worth investigating further, and in fact, mathematicians decided it was worth defining a formal notion for. And this is the notion of homotopy. So let me define for you what a homotopy is. So really a homotopy is a map, but it's a map between two functions. In this case, we're going to talk about loops. And it's a continuous function from the interval, across the interval, to your space X, such that at interval 0, you're evaluating to alpha, and at interval 1, you're evaluating to beta. If such a map exists, we write alpha is this symbol to beta. Really, this symbol is spoken as alpha is homotopic to beta, right? With that being said, let me tell you what this means in pictures, because it's way more fun that way. So what am I saying? I'm saying a homotopy is a map from this square, right? This is H. It's a map from the square to your space, where when you evaluate at this time block, it's alpha. Okay, so I have loop alpha. And when you evaluate at this time block, time interval, you get beta. But again, it's a continuous function. So there's not just this square with these loops. There's this square with a family of loops, where as I go across this interval, I get more and more loops. So I really foliate the space in between alpha and beta as I go around, as this time interval increases. And this is, again, in pictures, what it means for your space, for your two loops to be homotopic. Can I continuously deform with a family of loops one into the other? With this notion being given, let's go back and ask if our operations satisfy are satisfied up to this notion, is what I want to say. So is the loop product satisfied up to this notion? And the answer is maybe, maybe not, maybe sometimes. Let's see. So let's try again. Let's draw our square and investigate points at maybe different time points and see what happens. In this case, I've drawn for you the square, right? And I want to see if I can come up with a family of loops, continuous family of loops, that essentially interpolate these two loops, alpha and beta. And, you know, can I drag the tick marks? It's really the thing we want to try to do. Can I drag this tick mark somewhere, this one somewhere, and this one somewhere so that it looks like the loop above, right? Looks like this thing, this composition. And just as a note, you know, at time point a fourth, we're kind of on polar opposites of these loops. So the question is, does a homotopy exist? Can I drag the tick marks? Well, we're off to a good start. I can drag this tick mark up here and this tick mark up here, and that'll move my entire second half to my entire first half. So we're almost there. But what happens when I try to drag these two tick marks across? Am I going to be able to do it? Is it going to be continuous? And the answer is not really, no. If I tried to drag this tick mark across and this tick mark across, I'd have a problem because I wouldn't really be defining a function. I've already said that this tick mark is going to go here. And to define a function, I can't define one element to go two different places. I have to make a choice. Similarly here, we've already kind of decided that this is going to go here. So how can I also decide that it's going to go there as well? It wouldn't be well defined. So unfortunately, a homotopy doesn't exist. I can't find a continuous function where I can drag these tick marks, or I can't find a continuous function or family of loops that interpolates between the two loops. So unfortunately, the answer is no, again, sadly. But let's investigate the associativity, right? Can I get a homotopy for the two loops where I associate in a different order? This is the question now. And the answer we're about to find out, right? So again, the question, can I drag these tick marks across? And what's happening at these sort of time intervals, 1/4? In this case, 1/4 in the first loop, the left-hand side loop, right? I am right here back at the base point x0, right? Let me write it in. Where am I on the second one? Well, I'm halfway through alpha. So what do I do? Right? I can just speed up and get to the base point. And that's essentially what dragging this tick mark is going to do. And similarly with this tick mark. So I can do it. I can, in fact, drag across this square. And I can, in fact, get a parameter a one parameter family of loops interpolating this concatenation of loops. So that's great news. Finally, we've arrived at a positive answer. And it turns out this is no coincidence, and this is a really good sign to define something more general about our loop product, our concatenation of loops. So let me try to do that now for you. To organize all the things that we've kind of been seeing and try to make a definition or try to make something of it, right? So let's remember we have a binary operation. We can take two loops and make a new loop. And we called that star, pink star here. It turns out that when we work up to homotopy, right, when we use this, instead of using equality, we use homotopy, right, this new symbol I defined for you today. The operation's associative. We just investigated that. Turns out it also admits an identity. What does that mean? That means there's a distinguished element such that when I concatenate, there's a distinguished loop such that when I concatenate it with any other loop, it gives out itself, right? Spits out itself. And that loop turns out to be the constant loop. So if I run alpha twice as fast and then I stay fixed with the constant loop, that's the same as just having done alpha at its regular speed, or at least it's homotopic to that, right? Not the same. And it's also homotopic to first staying at the constant loop for half the time and then doing alpha. This is our identity sort of loop. And lastly, it also admits inverses. As you can maybe tell by the way I've been drawing these loops, there is some directionality to these loops. They have a way they go, right? And hence there's a loop backwards. And given that, when you loop concatenate these things, when you loop product these things, it'll give you something that's homotopic to the constant loop. So to just staying still, right? Staying here for the whole time block. And that's kind of not too hard to recognize, right? If I do alpha, which was going this way, and then I do the backwards thing right on top of it, that should be homotopic to the constant, at least intuitively, right? Great, so we have a binary operation satisfying all these relations. It turns out these relations, which I've written as equations, right, are the axioms for being a group. And turns out we can define something called the fundamental group at this stage. So I say pi 1 of x is really the loop space of x modulo this relation of homotopy, right? So I associate loops that are homotopic. If I can get a continuous deformation from one to the other, they're going to be in the same equivalence class, as we call it. And the operation in this group is loop concatenation, this loop product that I've defined for you. And you're probably wondering or asking yourself, Sophia, why'd you call it pi 1? What's up with that? And the answer comes on the following slide. And it's because it defines something called homotopy group. So if you have a different number than 1 there. So let me give you a different interpretation for this fundamental group. I told you it was the group such that you study all loops up to homotopy, right? Associated to like loops that are also homotopic to them with the operation star, right? Well, another way to think about it is the following. What's really the interval or functions from the interval where they have to be evaluated, where they have to start and end at the same point? Well, these are really functions from the circle, S1, to your space, images of the circle in your space. And that's exactly a way to think about the fundamental group. Think of functions from your circle to your space based at that base point. and then associate things that are homotopic, that admit this sort of continuous step formation. And that'll define a group for you, of course, with the same product as before. And this is exactly where you see one being represented. So you look at maps from the one-dimensional sphere, right, which is just the circle, to your space. If I wanted to look at something more general, for n positive and an integer, positive integer, you can study that as well. You can study spheres, maps of spheres to your space based at a point up to homotopy. And these will define for you another group, pi n, higher homotopy group as they're called. And that's a perfectly valid way of also studying your space. And this is really what modern topology is about, understanding these pi i's or pi n's for some n and for some maybe space x. Let's do some examples to demystify what pi 1 looks like for spaces that are maybe familiar to us. Namely, let's compute it for the sphere, right? So what happens when x is, excuse me, for the circle, the one-dimensional sphere. So what happens when we study x equal to the sphere and then its base point just being 0, right? Well, it turns out that's the integers with the group operation addition. It's very simple. And there's really beautiful proof, but the idea is all loops from here, right? All maps from the sphere to itself, right? So circle to itself are really determined by how many times you can twist the circle around itself. These are what loops are determined by when you look at them from the circle to itself. And it turns out has intimate relationships with the winding number. And that's exactly where this comes from. Let's investigate another example, namely the wedge of two circles, also known as the figure eight, with the base point being exactly where you wedged them, right? So this symbol symbolizes wedge. You wedge two circles. You identify one point on each of those circles, and that's your new space, your new topological space you're working with. And it turns out pi 1 of this can be written as pi 1 of one of the components, right? The circle, free product with pi 1 of the other circle, the second component of your wedge. And I already told you, and we sort of discussed, that each one of these is z with addition and then z with addition, right? The integers. And really, I wanted to discuss this sample because it's a manifestation of one of my favorite theorems in algebraic topology, which is the Seifert-Van Kampen theorem that tells you if you wedge, it tells you exactly how to compute pi 1 for spaces that either look like wedges or look like unions, and tells you that pi 1 can be written as something much simpler. And it has, it's been used since it was proven. I should say that Seifert and Van Kampen actually proved them separately back in the 30s, but now it's attributed to both of them. Anyways, I could talk about Van Kampen theorem all day. It's so fantastic and has really deep meaning beyond what we're going to discuss today, but I thought I'd mention it in this example. All right. I'd like to move on to talking a little bit about my research, though, what I do and what I've spent the last couple years working on. And it's the following. It turns out topological spaces are great and all, but they lack a lot of structure and a lot of rigidity in some sense. So we typically think of them as blobs and really like malleable things. But it's been understood and it's known that instead of studying topological spaces, you can study something called a simplicial set or simplicial sets. And these have much more richer combinatorial structure that we can work with. But in a sense, they are, spaces built out of points, edges, triangles, and tetrahedra, and higher versions of this that admit really nice relationships between sort of the dimensions of your faces and edges and triangles and so on. But recently, it's also been a hot topic, and I say recently, like maybe in the last 50, 60 years, topologists have been interested in studying spaces with a group action. So we understand homotopy and homotopy theory here pretty well. So the new challenge has been what sort of things happen when a group action is present. G has been assumed to be as general as a compact Lie group when we're studying here, but there are certain results where you need to restrict yourself to a more well-behaved group, mainly a discrete group or a discrete simplicial group. And my work has lied exactly in sort of the intersection of these two things, right? So I want the combinatorial structure that simplicial sets gives me, but I also want to study things with a group action. And this is where a lot of my work has been. And the last result I'll talk about today lies exactly here. I'm going to talk about some results here. I'm going to talk about some results here. And I'm going to talk about how when you combine these two, when you combine notions from these two areas, how you can get some interesting stuff there. Okay. So let's kind of do a crash course review of more general things that I discussed earlier. When I'm studying in topology, I'm really interested in maps between spaces, general spaces, and general notion is again homotopy, right? What does it mean for two maps to be homotopic? We're not just talking about loops now, we're talking about general maps between two general spaces. And it's exactly the same definition as before. Instead of working over the square, you just work over the interval and the space itself, right? Before, the space itself was the interval, so we got the square, but in this case, it's not the situation. And you ask it again at time interval 0, you're the first function, and at time interval 1, you're the second function. All well and good. You have a continuous family of functions that interpolate between these two functions. This is the general idea behind homotopy, continuous interpolation between two functions. We say something's a homotopy equivalence. I denote a HE here. If and only if you can find essentially an inverse, right? You can find a map going back such that its composition interpolates back to the identity in one direction and to the other identity in the other direction. This is a way to say two functions are homotopy inverses, right? So they're inverses up to homotopy. They're not exactly inverses, but again, I can find a homotopy to the identity. Great. Turns out this is a really strong notion of two maps being equivalent. This is still strong. But it gives you this really nice property that if your map is a homotopy equivalence, it gives you an isomorphism on these homotopy groups that I discussed before for all n larger than 0. That's really nice. And this is really what I'm interested in. This is the invariant that has boggled mathematicians' minds forever. So instead of asking for an inverse, let me just define a new notion where I simply ask, is there a map like this? And maybe I should also say the reverse inclusion is not true. If I had a map that just induced an isomorphism on pi i's, it's not necessarily a homotopy equivalence. And the classical example is the one I've drawn for you here. So there exist maps from, well, this is called the topologist circle or topologist sine circle, where you have the topologist sine curve here, and then you connect it to be a circle. This is a notoriously poorly behaved space, but it provides a lot of counterexamples and motivates a lot of definitions. So, you either love it or you hate it. But any map from this sort of space to the point turns out to be exactly this sort of map. It'll induce a isomorphism on all pi i's. But it's not a homotopy equivalence. I can't get a map backwards such that when I compose it, I get the identity in either direction. Just can't find it. So that's what motivates, right? I don't have an inverse. That's what motivates the following definition that I'm going to give, which is that of weak homotopy equivalence. So let me just define a weak homotopy equivalence to be exactly what I said, right? I want it to be a map that induces an isomorphism on all pi i's. And this might seem rather hard, or it might not seem like there are lots of maps like this, but I'm here to tell you that at least for spaces that topologists have generally cared about, it's not so hard to find. In fact, a theorem of Whitehead says if your spaces are CW complexes, right, these are spaces built out of cells, then a homotopy equivalence is a homotopy equivalence if and only if it's also a weak homotopy equivalence. Right, so on special objects, the two notions coincide. And if you assume even nicer properties about your space, if these x and y are simply connected, this means pi1 is trivial, then f is actually also a z homology equivalence. This means that when you take the induced map on homology with coefficients in z, it's an isomorphism on all homology groups. Fantastic. This was proven in Whitehead's very groundbreaking paper in 1949. He had two groundbreaking papers that year, and that's where you can find these sorts of results. All right. Given this review, I'd like to talk about simplicial sets, right? I said I want to talk about simplicial sets, and I want to talk about topological spaces with group actions. So let's talk about new math. If I consider a new notion of equivalence on simplicial sets, mainly reduced simplicial sets, that's what this little 0 here stands for. And reduced just means that at level 0, I only have a vertex. I define a map of two reduced simplicial sets to be a pi1r equivalence, where R is any commutative ring that you'd like. If and only if, when you geometrically realize your simplicial set to be a topological space, the induced map on pi1 is an isomorphism, and after geometrically realizing at the level of universal covers, that's what this bar says, the map on universal covers induces an isomorphism on all homology groups with coefficients in this ring R. So that's where the dependence on the ring comes in. This looks like perhaps the most exotic notion of map that you might think of. But it turns out if you start plugging in, rings that you like, it might not seem as exotic. So let me just say something that I proved in my thesis. When you take R to be exactly the integers, you recover the notion of weak homotopy equivalence for this geometrically realized map. So it's different and it's weird, but it's not as different and weird as you might think. This is exactly the thing that I was defining before, right? A map is a weak homotopy equivalence if it induces an isomorphism on all homotopy groups. Turns out when z equals r in this setting, you can prove that that's true. A remark is, well, when you take r equal to the rationals, this new notion actually recovers rational homotopy theory. I abbreviate it RHT. And this is a theory that's been studied by many of the greats, some might say, in mathematics, Quillen being one of them, Sullivan being another one. And this is sort of a very understood area and is recovered by the work that I'm going to kind of describe for you today. So what I'm doing is more general than rational homotopy theory. And it turns out, due to Sullivan's fracture theorem, which is a theorem that says if we can understand the homotopy theory or the homotopy types of spaces over Q and over FP, right, the field with prime elements, then that'll inform us about what happens over the integers. So this is sort of motivating the fact that really the R I want to plug in here is FP, and I want to understand things p-adically. But that's an aside. That's a conversation for another day. The theorem that I want to bring to your attention today, as it turns out, is when R is an algebraically closed field, a reduced simplicial set can be recovered up to this notion that I just defined for you, pi1r equivalence, by its simplicial coalgebra of F chains. And this is up to a suitable notion of equivalence of coalgebras, right? This is a really interesting theorem because it's saying I don't really have to know much about the space. I can just study something algebraic, a coalgebra, in fact, and I can get all the homotopical information that I need with respect to whatever ring I want to work over, and it's there algebraically. I emphasize that we're talking about coalgebras or simplicial coalgebras because it's the right amount of algebraic structure to study your space. Groups are not good enough. Rings are not good enough. You really need something really robust with a lot of operations to get what you want. In a coalgebra, you can think of it as an R module, or you can think of it as an algebra, but instead of multiplying things, you have a coproduct. You break things apart, right? Great. This is everything happening without a group action. What happens when you incorporate a group action? Well, this work now lies in the area of equivariant homotopy theory. And if I give you a group, any group, I say it acts on a space if I have a map from G cross the space to the space to it, like back to itself. And now I can run the same sort of arguments and the same sort of discussions that I had before. I say the maps are equivariant if it respects the group action again, right? So we need things to be preserved. If I'm going to introduce a group action, it better play nice with everything else that's going on. So let me give you a quick example because I think it'll be rather enlightening and we'll get to the motto. If I give you, for example, this space, right, delta 2, this simplex, and I say it has an action of S3, the symmetric group on 3 elements. I've drawn for you sort of the subgroup lattice here. A way to understand this space is to look at what moves or doesn't move. In this case, it's what doesn't move, to understand the fixed points of this space under subgroup actions. And I've sort of listed them kind of small here, but you can kind of deduce what's happening. If I flip 1 and 2, what stays fixed? 0. If I flip 2 and 1, excuse me, if I flip 0 and 2, what stays? 1, right? And so on and so forth. And this is all to say that incorporating this information of fixed points is really the way to understand G homotopy equivalence, G weak homotopy equivalence, and a G version of Whitehead's theorem. So all the notions that I described earlier still exist in this setting, but they need to be adapted appropriately. And the way we adapt them appropriately is by really studying fixed points, defining things in terms of fixed points. And the motto is, as I've written it here, study the fixed point spaces. If you want to understand something that has a group action, you can flip it, you can rotate it, you can twist it, and so on. If you want to understand something like that, a good way to understand it, a good way to understand that thing's homotopy, is to study the homotopy of the things that don't move under all possible subgroup actions, right? This is a collection of things that you can study its homotopy, and it'll give you information about the larger thing. So this is the motto. This is the way to internalize equivariant homotopy theory. So let me talk about my research. This is the last result I want to give. If you consider a new notion of equivalence on G reduced simplicial sets, if that's what you want to call it, this is going to be a map similar to the one as follows. I have 2 G simplicial sets, and I say that a map between them is a G pi 1R equivalence if for any subgroup, the induced map on fixed point spaces, for every subgroup is a pi 1R equivalence, right? I just asked that the induced map on fixed point spaces is the same as before. What does that mean? That means on fixed points, once you geometrically realize, you have an isomorphism on pi 1s, and you have an isomorphism at the level of universal covers on homology groups. Fantastic. This is exactly following the motto that I gave before and incorporating this more general map that I discussed earlier. A claim is, again, you can recover R, when R is equal to the integers, you can recover the notion of G weak homotopy equivalence. Fantastic. We're exactly on track as before. And it turns out we get a theorem similar to before, that when R is equal to an algebraically closed field F, and you study a reduced simplicial G set, this can be recovered, again, up to this notion, by its simplicial coalgebra of equivariant F-chains. So now we have to define a new notion of what equivariant F-chains are. But it turns out it's going to be a simplicial coalgebra, and there's going to be a suitable notion of equivalence between these coalgebras once more in the equivariant setting. So this has been a really interesting avenue of research for a variety of reasons. It turns out we do understand, we really do need this to be a field to understand what happens on the coalgebra side. And we can get as general as studying perfect fields. So we have a result similar, not quite as good, but similar to this one when F is more generally a perfect field. And as I mentioned earlier, we want to study things like R equal to FP. So even though it might not be entirely recoverable, the space might not be entirely recoverable when F isn't an algebraically closed field, we know the failure of things not being recoverable. So that's all I want to say with respect to this theorem and this work. If you're interested in learning more, you can find it in our preprint. If you're interested in learning things of the non-equivariant setting that I described, this paper of Raptis and Rivera is really good. If you want to learn more homotopy or equivariant homotopy theory specifically, there's a set of class notes by Bert Guillou that are really good that I liked learning from. And if you want to learn algebraic topology more generally, a classic text is that of Hatcher. And I think that's all I wanted to say. Thank you for your time. And I hope to hear and talk more. If you are interested, please contact me. Thank you so much.